So due to some personal reasons and technical reasons, we could not upload any video in the last week and last week. So it will continue from now. From now we will upload continuously. So as I have said in the previous session, in this lecture session we will see some examples of some computations regarding continuous functions and uniform continuous functions. So let me first recall the notion of continuous function. So I have a subset of R and a map from U to R. I fix some element A belongs to U. We say that this map F is continuous at this point A if given epsilon positive, there is a delta positive such that whenever x belongs to A minus delta and A plus delta, we should have f of x in f of A minus epsilon, f of A plus epsilon. This is something as saying mod x minus A is less than delta. This is something as saying mod fx minus fa is less than epsilon. So this is about continuity of the function f at this point A. So let us do some example. So consider the function f from R to R. The function x is going to root x. See, whenever I want to talk about root x, I cannot take negative elements here. So here I am restricting my attention to the case where the domain is R positive, which means a set of all positive real numbers including 0. So now we are trying to see whether this is a continuous function or not. Is it continuous function or not? Let us fix some element A in R positive and then see whether we can produce given epsilon positive, can we produce a delta positive with these properties. This implies this. Okay, let us fix some epsilon positive. Now we are looking for a delta positive with certain conditions. Now what do we want is the following: whenever x minus A is less than delta, we want fx minus fa to be less than epsilon. So let us at least write down what this really means. Fx and fa, the function f is given as x goes to root x. So let us replace x and fa by root x and root a. So root x minus root a less than epsilon. So what we want is, given epsilon positive, we want this condition: x minus a less than delta implies root x minus root a less than epsilon. We are looking for such delta. Now see, here we have a root a and a root x. So let us write down this in the following way: mod x minus a, this I am treating as say p square minus q square. P is root x and q is root a. So p square minus q square is p plus into p minus a. So this I am writing as root x plus root a times root x minus root a. This we are writing in this way. So this is less than delta. So whatever I have written here, I am writing the same thing here. So now the situation is the following: given epsilon positive, we are looking for a delta positive such that whenever we have this condition, that should imply this condition. Observe some similarity between these two conditions. There is a common part in these two inequalities. This part is common, root x minus root a is common in both cases. So let us just remove this and send it here. So what do we get? Mod root x minus root a is less than delta by root x plus root a. Again there is a mod. See, whatever the elements x we are taking, this is positive. By definition, root of some element is already positive for us. So we have this inequality. So root x plus root a is always greater than root a. Mod is not necessary, but still we are this. So this implies what? This implies 1 by root x plus root a is less than 1 by root a. So I have this extra term, I want to get rid of that. So this is the approximation that I am making. But if I have to write in this way, I need to know before that this element A is non-zero, but whatever you have started with, this element A can be 0 also. A belongs to R greater than or equal to 0. So what we do is let us change this something here. So let us assume that A is non-zero and proceed further. So then this makes sense. If A is non-zero, this makes sense. So let us then what do we do for the case A is equal to 0? We can do it as a separate case. So for every A non-zero, one can talk about this inequality. So let us replace this 1 by root x plus root A by 1 by root A. Is less than delta by root A, just that. So now what we want is, we want, see this is fx minus fa, we want this to be less than epsilon. What we have here is delta by root A. Suppose delta by root A is just epsilon, then we can just replace this by epsilon. So this is something as saying delta is equal to epsilon times root A. So given epsilon positive, if we take delta to be epsilon times root A, then for any x belongs to R positive with x minus A less than delta, we have root x minus root A less than epsilon. So this says this function f, whatever I have defined here, is continuous at every point A that is non-zero. So what do we do for A equal to 0? For A equal to 0, one cannot do this step. That is the only problem. Because A is suppose A is 0, one cannot talk about 1 by 0. So we have to make we have to look for other alternative idea. So what we want is this: whenever x is x minus 0 is less than delta, we should have fx minus f0 less than epsilon. So what is fx? Fx is just root x, x minus 0 is just 0. So mod x less than delta should imply root x less than epsilon. See, this is equivalent to x less than epsilon square. Why? Because these two are positive terms, a less than b should imply a square is less than or equal to b square. So this is always true. If a less than b, then a square is less than or equal to b square. But if this is true, we have this condition. So instead of asking for root x less than epsilon, one can simply ask that x less than epsilon square. So one thing to observe is the following: we are looking for a delta such that mod x less than delta implies x less than epsilon square. So this also actually one should write down mod here, but as I said, x is already positive. X is already positive, so mod is not necessary, but otherwise you should be putting mod. So one nice choice for delta is just epsilon square. Just take delta to be epsilon square. Then whenever x belongs to R positive is such that mod x is less than delta. So this is what this is same thing as because delta is equal to epsilon square. This is less than epsilon square. Again, as I said, this implies root x is less than epsilon, and this is what we want. F of 0 is 0 here, so I'm not writing that. So this says this square root function f from R positive to R given by x goes to root x, it's continuous function on the domain of that function. So but we had to do two cases. If for a positive there is a, for a non-zero there is a different idea, for a is equal to 0 there is a different idea, and yeah, so that's about continuity of a function, continuity of square root function. Okay, so let us do one more example. Consider the function f, x goes to 1 by x. So here of course when I allow 0 here, I don't know what to write for 1 by 0. So let us consider the case when only positive real numbers. not even 0 is not included here in the domain. So now let us look for the continuity of this function. Is it continuous? So again what do we need to do is let us fix some element a belongs to R positive, then see if given epsilon positive, do I get a delta positive such that whenever mod x minus a is less than delta, fx minus fa should be less than epsilon. This is what we are looking for. Now let us just replace fx by 1 by x, fa by 1 by a, and then see how far we can reach. So 1 by x minus 1 by a, this is same thing as x minus a by x a. Because x and a are both positive, one can actually get rid of this this mod unnecessary. Now x minus a, see we are looking for a delta positive with this implication. Let us assume we have got a delta, and then see how far what are the properties that delta should have, so that might give you some idea of what delta should you declare. So let us just write this in mod x minus a is less than delta, and this I don't know what to how to change it, so I am leaving it as it is. Now x minus a less than delta is what? This means minus delta less than x minus a less than delta. So this is same thing as saying a minus delta is less than ax, and x is less than a plus delta. So this implies 1 by x is less than 1 by a minus delta. This implies 1 by a plus delta less than 1 by x. See, here we are assuming that none of them are 0, otherwise I don't know what it means. So one nice thing to observe here is there is a x component here, there is 1 by x component here, and we suppose we got delta, then we can replace 1 by x, we can approximate 1 by x by this inequality. So what we do is we replace this 1 by x part by 1 by a minus delta. So this is less than delta by a minus delta times a. So this same thing as delta by a square minus a delta. Now what we want to get that fx minus fa is less than epsilon. What we got is just this. Suppose this quantity is less than epsilon, then we are done. Fx minus fa is less than this. Suppose delta is this component is less than epsilon, then we are done. Less than or equal to. So one nice trick to do is just declare that this is equal to epsilon, and then see whether we can write down delta in terms of epsilon and a. So we are looking for delta by a square minus a delta to be equal to epsilon, and this is something as delta is equal to a square epsilon minus a epsilon delta. This is same thing as what? Delta plus a epsilon delta is equal to a square epsilon. Again what this is same thing as delta times 1 plus a epsilon is equal to a square epsilon. This is delta is equal to a square epsilon by 1 plus a epsilon. See, it should be clear what I am trying to do here. I am just trying to see that if there is a delta, satisfying this property, then we should be getting this quantity. But what we want is we want it to be less than epsilon. Suppose this is equal to epsilon, then also we are done. There is a less than symbol here. So we are done. So now I am declaring. So now I am declaring that this quantity is equal to epsilon. That's what I have written here. Then some obvious computations. So I am just pulling this here. So delta is equal to epsilon times a square minus epsilon times a delta. Then I am just pulling this here. So delta plus epsilon delta is equal to a square epsilon. I am just taking the delta common, 1 plus epsilon is equal to a square epsilon, and a and epsilon are both positive. So this is non-zero, so I can write down this. So given a for delta is equal to this, we would have this inequality. 1 by x minus 1 by a is less than epsilon. So this is not just idea, this is actually complete proof. But you can write down, you can write down some more details, as in suppose x minus a is less than delta. Just from here replace delta by this quantity, and just from here you can write down, you can conclude that 1 by x minus 1 by a is actually less than epsilon. I have added some details in the lecture notes, you can see that. But before seeing, you can try to write down your own idea. Just replace delta by this quantity here, and then conclude that this is the case. 1 by x minus 1 by a is less than epsilon. So this says what? This says the function f defined as x goes to 1 by x is continuous on the domain. I fix the point a belongs to r positive. Then we have seen that given epsilon there is the delta positive, such that whenever x minus a is less than delta, we have f x minus f a is less than epsilon. So this is about continuity of the function. Continuity of the function x goes to 1 by x. So let us do some more examples. Maybe now we will do the sequence version of continuity. In last two examples we have used epsilon delta definition. Now we will use the sequence version of continuity. So let us take the following sequence f from r to r, defined as the following: f x is equal to x if x belongs to if x is a rational number, 1 minus x if x is a irrational number. So let us see at what points of the domain of R is this the continuous function. R is the continuous function on the whole domain, or is it nowhere continuous? So we will see. Now let us fix some element a belongs to R. Then we have to see whether this function is continuous at this point or not. So now we are trying to use the sequence version. So given a belongs to R, because rational numbers are dense, there is of course a sequence in Q that converges to A. Now what we need to check is, we need to check if f of xn also converges to f of A or not. Now because xn is an element of Q, fxn is same thing as xn. So one can maybe I will write down separately. So this is same thing as the sequence xn. No, so I already said it converges to A. So this converges to A. Now suppose A is a rational number, then f of A is same thing as A, and we are done. So suppose A belongs to Q, then we are done. For a rational sequence that converges to A, we have fxn converges to f of A. Suppose A is an irrational number, then fa is 1 minus A, and these two cannot be equal. 1 minus A is equal to A should imply A is equal to 1 by 2. But as I said, A is irrational. If you assume A is irrational, then these two are not equal. So if A is an irrational point, this function cannot be continuous at that point. So now what is remaining for us is to look for continuity at rational numbers. So let us take A to be a rational number. Now suppose we take a rational sequence that converges to A, then as I said just now, fxn is same thing as xn, then f of A is same thing as A, and we have the correct convergence. Now there may, even if x is a rational number, so there may be a sequence of irrational numbers that converge to this element a. So xn converge to a, but these xn's are elements of r minus q. In that case, what is f of xn? That is 1 minus xn. So now this is the sequence. This should converge to what? Xn goes to a, 1 minus xn should go to 1 minus a. But again 1 minus a is for 1 minus a to be equal to a, we want a to be half, otherwise there is no choice. So what does this say? This says this function f is continuous only at this point half. Otherwise, see, for irrational numbers, we have seen that there is absolutely no choice. For irrational numbers, we have already seen here that there is no way that f can be continuous at that point. For rational numbers, there are two possibilities. One should take a sequence that that consists of only irrational numbers. That's what you have taken here, and the corresponding image sequence is 1 minus xn, and that converges to 1 minus a. But for 1 minus a to be is equal to a, we want it to be equal to half. So if a is not equal to half, then these two are not same. So that doesn't satisfy the notion of convergence of sequences related to continuous functions. So this function f is continuous only at one point, that is half. Okay. Now let us do some example related to uniform continuity. So let me just recall the definition of uniform continuity, both the sequence version and the epsilon delta version. So let us take a subset of R and map from U to R. What does it mean to say f is uniform continuous on the domain U? Whenever given epsilon positive, there is a delta positive, such that whenever x and y elements of U are with this property, the corresponding image fx and fy have this property. Fx minus fy is less than epsilon. So this is the notion, this is the definition for uniform continuous functions. U subset of R, f from U to R is said to be uniform continuous if given epsilon positive, there is a delta positive, such that whenever x and y in U are of this property, x minus y less than delta, then we should have fx minus fy less than epsilon. So this is actually y. Now what is the sequence criteria for uniform continuity? So for two sequences xn and yn in U with the property that xn minus yn, the difference of the sequence, converge to 0, then the corresponding images of these two sequences, one is fxn, other is fyn, this difference also converges to 0. So this is how we define uniform continuity of a function on the domain on this domain U. Now let us do some example let us take some function and then say whether it is uniform continuous or not. Okay, so let us take the function f from R to R, x goes to 1 by x. So now we are looking for uniform continuity of this function. So what we do is we take two sequences in U whose difference goes to 0. We should check the corresponding sequences, the difference goes to 0. So in 0 1, what sequence that you can think of? I only know one sequence, that is 1 by n. 1 by n is a sequence inside 0 comma 1. It converges to 0, but 0 is not an element of 0 comma 1. But see, as I said, observe, I did not ask that xn is convergent sequence. I only took any two sequences whose difference converges to 0. This need not be an element of U itself. So that is the difference between continuity and uniform continuity. In continuity, what we want is, we want xn converge to A should be an element of U, fxn converge to f of A. So it was about just single sequence, but here we are taking two sequences, none of them has to be convergent, that is the whole point, none of them has to be convergent. So here I am taking the sequence 1 by n that converges to 0. So I should look for a other sequence so that the difference converges to 0. So as I said, only sequence that I can think of in 0 comma 1 is just this sequence. So maybe I should just change it slightly and then see if the difference still goes to 0. So let me take the sequence 1 by n plus 1, this also goes to 0, this is convergent, but the question is the difference a convergent sequence? So let us check that. So 1 by n minus 1 by n plus 1, what is this? This is n plus 1 minus n by n times n plus 1, this is 1 by n times n plus 1, oh nice, this goes to 0 anyways. So we have two sequences, 1 by n and 1 by n plus 1, two sequences inside this 0 comma 1 such that their difference goes to 0. So this is a appropriate candidate to check uniform continuity. Now what is f of xn? F of xn is f of 1 by n is just n. What is f of yn? F of 1 by n plus 1, that is equal to n plus 1. So this difference is 1, it is a constant sequence. This constant sequence 1 is not converging to 0. So for this function we have seen that there are two sequences inside 0 comma 1 whose difference converges to 0, but the corresponding images, here the corresponding image sequence is n, here the corresponding image sequence is n plus 1, the difference is just the constant sequence 1, this constant sequence 1 is not converging to 0. So this says the function f is not continuous, the function f is not uniform continuous in this domain. Yes, so that is all about today's session. It was supposed to be just doing some 3-4 examples, and in next session we will see, maybe I will add more examples in the lecture notes for regarding this uniform continuous functions and all that. So in the next session we will see something about differentiability of a function, and yeah, that is the starting point of next part. That's all.